Hello everyone. I am excited to present our paper, ViT3, Unlocking Test Time Training in Vision. Let's get started. We are now entering the long sequence era. Applications like embodied AI and video generation push models toward longer inputs and denser tokens. But the challenge is clear. The computation of transformer scales quadratically with sequence length, and that quickly becomes too expensive. The root of this quadratic cost is the softmax attention mechanism, which computes similarities between every single query and key. To fix this, the community introduced linear attention, which drops the softmax and reorders the matrix multiplication to achieve linear efficiency. But today, let's look at this from a completely different angle. Traditionally, we view attention as a weighted sum of tokens. Here, we view softmax attention as building a two-layer MLP using K and V. Here is how it works. We take Q as the input. Our first linear layer is the transposition of K. We apply a softmax activation, multiply by the V matrix, and get our output. Linear attention does a similar thing, building a single linear layer using K and V. In other words, attention is simply the process of building a model with K and V, and then applying that model to Q. So if both are building models, what is the fundamental difference? The answer is compression. Softmax attention does not compress K and V. It has incredible expressiveness but terrible efficiency. Linear attention applies coarse compression. It gives us great efficiency but loses vital information. Therefore, sequence modeling is all about how we compress context. What we truly want is accurate compression, a method that is compact, highly efficient, and expressive. But how can we achieve that? We look at deep learning itself. Deep learning is arguably the most powerful compression algorithm we have. It can compress trillions of data points into a compact, highly structured model. Very accurate and very successful. This is where test time training, or TTT, comes in. The core idea is to bring the magic of deep learning into sequence modeling. Specifically, TTT views the key value pairs in a context as a mini dataset. During inference, it uses fast, self-supervised online learning to train an inner model on this dataset. This compresses the contextual information right into the inner model's weights. Once trained, we simply apply this adapted model to our queries. This opens up a design space that is far richer and more powerful than traditional linear paradigms, offering a promising path forward for scalable long-sequence modeling. However, the very flexibility of TTT introduces a critical bottleneck, a large and underexplored design space. Key choices regarding the inner training process and the inner model architecture lack systematic understanding, which prevents the design of powerful visual TTT models. Therefore, the goal of our work is to establish design principles for building efficient yet expressive TTT models. To do that, we systematically explore the TTT design space from 6 aspects. Through extensive experiments, we distilled 6 practical insights that will serve as a guide for effective visual TTT. Let's walk through what we found. Let's start with inner training. The first point, the inner training loss must have a non-vanishing second derivative. In TTT, we have to differentiate through the inner training steps to optimize the value projection. If that second derivative vanishes, the value projection simply cannot be optimized. As you can see in our results, L1 loss yields the worst accuracy for exactly this reason. Smooth L1 also struggles in certain regions. But other losses without this issue easily hit around 79% accuracy. Next, we have 2 key observations. First, a single epoch of full batch inner training works well in vision. While sequential mini batches work great for causal data like text, they introduce a causal bias that harms non-causal vision tasks. And while multiple epochs improve accuracy, they slow things down without specialized implementation. Second, a large inner learning rate of 1.0 is effective. Small learning rates don't update the weights enough to capture the context, while excessively large ones cause the training to crash. 1.0 is the sweet spot. Now let's talk about the inner model architecture. Insight 4 is simple, wider is better. Increasing the inner model width consistently improves performance. This is a key advantage of the TTT. It allows for a more complex nonlinear module as the inner model, and consistently benefits from its capacity. However, there is a trade-off. At test time, an inner model requires a forward pass on K, a backward pass, and a forward pass on Q. This means it costs about 4 times the compute of a standard outer module. So, while scaling width works, we believe designing lightweight and expressive inner models is an important topic. One might assume that if wider is better, deeper would be better too. However, we observe that deep inner models currently suffer from severe optimization difficulties. Specifically, in our experiments, deeper inner modules actually led to higher training loss and lower test accuracy. We attribute this problem to 2 aspects. First, the outer network struggles to learn a good initialization for a deep inner model. Second, deep inner models suffer from vanishing or exploding gradients during the fast inner loop updates. We all know deep networks possess incredible capability, which is a key factor of deep learning. So, solving this optimization challenge for deep inner TTT models is one of the most exciting open research directions we identified. The last insight. Convolutional architectures are a perfect match for visual TTT. While previous TTT works used channel-wise modules like MLPS, we found that convolutions are particularly elegant here. The online trained kernel weights store the global information from all key value pairs, while the sliding receptive field naturally handles local models. This delivers a natural integration of global and local features, and enables significant performance gains. Based on these findings, we build ViT3, a pure TTT baseline with linear complexity. We evaluate ViT3 on a broad suite of tasks. ViT3 matches or outperforms various advanced linear complexity models. Compared to vision transformers, our ViT3 scales more efficiently in throughput and memory consumption. Finally, here are some takeaway messages to summarize our work. That's all for our work. Thanks for your listening.